Those are the most important neurons only for the original class, giant panda, which means they are highly activated by benign giant panda images. The blue nodes are important neurons only for the target class, armadillo. The orange nodes are the most important neurons for both original and target classes, giant panda and armadillo. The red nodes are the neurons that are highly activated by only successfully attacked images. These neurons are exploited by the attack to induce the incorrect prediction. By exploring the activation pathways, PGD successfully perturbed pixels to induce the brown bird features, an appearance more likely shared by an armadillo than a panda. Both armadillo and brown birds have small, roundish, and brown bodies. The brown bird neuron then contributes to the armadillo misclassification by activating more features such as scales, bumps, and mesh. By using the options in the control sidebar, users can interactively filter the neurons and connections to visualize. For example, they can select to visualize all graph, or only highlighted neurons, or only pinned neurons. By using the Highlight Pathways options, users can select which activation pathways to visualize, such as most activated or most inhibited, excited, or most changed by the attack. By using the comparison mode, users can compare how attacks of different strengths have different activation pathways. In summary, we developed Bluff, an interactive system to understand how adversarial perturbations flow of the learning model. Bluff visualizes most activated, inhibited, excited activation pathways after the attacks, and provides flexible comparison of attack escalation. Thank you all for listening. I'm happy to take any questions.
Hello, good morning, everybody. Good afternoon, good evening, and welcome to this session on immersion. My name is Manuela Waldner. I'm from Thu Oct, and we have 6 exciting papers in this session dealing with various aspects of visualization in virtual reality and augmented reality. Please post your questions to Discord and YouTube. And we start with the first presentation, which is called Shared Surfaces and Spaces, Collaborative Data Visualization in a Co-located Immersive Environment. And the paper will be presented by Benjamin Lee from Monash University.
Hello everyone, my name is Benjamin Lee, and I'll be presenting our work on collaborative immersive analytics in a co-located virtual environment. It is well known that collaboration plays a significant part in the exploratory data analysis process. Researchers have poured significant efforts and resources into collaborative visualization environments, such as large cave setups and shared tabletop environments. As immersive virtual and augmented reality head-mounted displays, or HMDs for short, become more commercially available, researchers have begun exploring how these devices can be used to facilitate collaborative immersive analytics. For example, work by Butcher and colleagues on the left use immersive HMDs to visualize 3D parallel coordinates visualizations on the top of a shared interactive tabletop. On the other hand, work by Sun and colleagues on the right use augmented reality to provide private views of sensitive information overlaid on top of a shared wall-sized display. However, existing work has thus far coupled these 2D displays and the augmented reality 3D space in specific ways for very niche purposes, such as to facilitate interaction or enable private workspaces. These works are only a subset of many possible configurations of collaborative immersive environments, where they force users into set analytical workflows that are essentially dictated by the setup. It is not yet clear how users will organically make use of these 2D surfaces and the 3D space, particularly when there's no set workflow or functionality enforcing the use of either one. For example, what if data visualizations could be created and manipulated in either space or on the surfaces, rather than being confined to only the wall display? To this end, we sought to investigate how users behave in an immersive collaborative visualization environment in which they can freely choose how to utilize the surfaces and the space around them. To do so, we designed and developed Fiesta, the free-roaming immersive environment to support team-based analysis. I will now play an excerpt from our supplemental video to quickly demonstrate the system. In this research, we present a user prototype we call Fiesta, the free-range immersive environment to support team-based analysis, in order to explore how users collaborate in a shared, physically co-located virtual environment, where users are free to choose where they work. Fiesta is built around 3 main design requirements. Fiesta uses the Immersive Analytics Toolkit to support basic visualization tasks accessed by a two-dimensional panel. This panel allows users to author visualizations which they can then position in the space around them. The panel itself can be moved, allowing users to dictate where and how they work. Fiesta has baseline data visualization functionalities, allowing users to perform operations such as binding dimensions to visual variables like size and color, specifying linking attributes for time series style visualizations, and faceting the data by dimension. Users can also inspect data points using a Details on Demand function. Fiesta is a shared environment, with each user represented by a virtual avatar and everything being shared and interactable by everyone to allow for workspace awareness. It was deployed on tetherless VR backpacks, allowing free roaming in the room-sized environment. Fiesta uses virtual walls to act as boundaries of the room. To further explore the surface metaphor, we include a virtual table in the center of the room. These surfaces resemble their real-world counterparts, with users able to place visualizations onto them at will. Fiesta also introduces a number of novel features to support collaborative visualization, such as shared authoring panels supporting tear-out-style duplication of visualizations that can be scaled and positioned freely on the surfaces or in the space around the user, rushing of data points with both shared and private modalities, tools for annotating visualizations, and support for an arbitrary amount of users in the immersive space in both co-located and remote contexts. The source code is available in a public GitHub repository, as seen on screen. The link is also available in the manuscript. We used Fiesta to conduct an exploratory study into how users may behave in a free-roaming collaborative immersive analytics environment. In total, we recruited 30 participants from our university's faculty, who are a mix of postgraduate students and academics. We first began our study with 5 groups of 3 participants in what we refer to as Part A. In Part A, we had only enabled 2D style visualizations with no option to use the Z-axis, as well as not included the table at all. We then followed this with the other 5 groups in Part B. where both Z-axis 3D visualizations and the table were enabled. We chose to do Part B in order to observe a greater variety of user behaviors. Everything else was kept as identical as possible. We began each session with an introductory briefing and training on how to use Fiesta. Groups were then given a series of directed tasks and open-ended free exploration tasks to perform as a group using a multivariate dataset of real estate auction data, with a designated rest period in between. They were then told to do this exploration using any strategy they wished, but were not given any tips and/or suggestions as to how to best work together. In addition, we instructed them to present their findings at the end of the free exploration task to a virtual audience member or observer that we remotely controlled via mouse and keyboard. This culminated in a post-study questionnaire, where each participant in the group was asked to respond individually without any group discussion. Each session lasted approximately 90 minutes in total. We collected user tracking data that was logged by Fiesta, video and audio recordings of the study, as well as questionnaire responses from all participants. The questionnaire asked both Likert scale and short answer questions relating to immersion, cybersickness, and their perceived collaborative behaviors. We then analyzed the data using an open coding methodology with 3 of the authors, as well as performed visual analysis to identify any further insights from our data. Due to the exploratory nature and novelty of the work, we decided to focus our analysis on 2 high-level categories. First, how Fiesta was used by our participants. This is in terms of general system usability, the roles in which the services played, and the manner in which visualizations were organized in the environment. Second, how groups collaborate, divide the space, share resources, and share findings with each other in the environment. I will now highlight the most relevant findings from our study. Firstly, how did participants end up using Fiesta? To begin with, it was clear that our participants were more than capable of performing visual analytics using Fiesta. Participants were engaged in tasks in VR for an average of 45 minutes, with most reporting that they felt immersed in the virtual environment, and most reporting little to no cybersickness in the questionnaire. However, it should be noted that Fiesta is still missing many advanced visual analytics and functionalities, such as textual queries, which our participants had commented on in their questionnaire responses. We observed that the vertical walls were predominantly used for organization, storage, and presentation. However, the extent to which they were used was dependent on the available visualization types, namely the presence of 2D and 3D visualizations. A majority of participants kept to planar-like layouts in Part A, as the nature of 2D visualizations meant it was a natural location to organize their work in a grid-like fashion as you see on the screen, despite requiring more physical movement and effort to do so. In contrast, only one participant in Part B used this layout. Those in Part B were instead far more likely to use egocentric style layouts when 3D visualizations were introduced, with both 2D and 3D visualizations placed in a spherical fashion around them. In these cases, the vertical walls were used far less often, except during presentation, which I will address later. This suggests that different placement tools and/or functionality is needed to accommodate each visualization type in immersive environments. In contrast to the walls, the virtual table was only used by a single group. This is most likely due to the intangibility of the table and the lack of gravity, making it not seem that all useful to our participants. Other groups simply place their visualizations wherever most convenient during group work, usually at around head height. While extra effort was spent by participants to properly utilize the walls for both analysis and presentation, participants were not willing to do so for the table. This suggests that it's simply not enough to provide a designated shared tabletop workspace, with there needing to be some express purpose and/or functionality for its existence, be it an alternative authoring interface or by enabling touch input. Secondly, how did our participants divide, share, and work together to find and present insights and data? These heat maps show the physical locations on the participants and the tables throughout the course of the tasks. Groups tended to equally divide the room into personal territories without explicit negotiation. These acted as physical areas in the environment where they could comfortably move around and work individually without any intrusion, and were implicitly defined by both their physical movement and object placement. Group territories, on the other hand, were not as common, as resources typically did not need to be shared between group members. In many cases, participants would observe and discuss their findings simply by remaining in their personal territories and looking from a distance. There were some exceptions to this, however. For example, Group 7 have here and on the screen have converged together into a single group member's workspace to work together for a prolonged period of time. In these instances, participants were equally willing to interact with and utilize each other's objects, as there was often a common shared interest. In most cases, however, participants would simply direct each other to perform some tasks, such as to switch to some specific dimension for a visualization. In regards to workspace awareness, many of our participants consciously made clear to keep their work as visible as possible to the group members, favoring it over privacy. Panels were overwhelmingly oriented facing towards the center of the room, with participants oftentimes rotating on the spot in order to keep track of each other's work. Lastly, when groups were asked to present, we observed that presentation quality changed dramatically amongst participants, even within the same group. Some would engage with the audience avatar, maintaining consistent eye contact and hand gestures such as on the left, while others would ignore the audience altogether, such as on the right. This is despite the same groups making a conscious effort to reorganize their visualizations before presentation, even in Part B with egocentric layouts. Of note is that almost all participants did not account for the audience's viewpoint and perspective, clearly causing issues like parallax on 3D visualizations. It may be that our participants simply did not anticipate the need to do so, or that better tools are required to support this need. In conclusion, some high-level takeaways and subsequent future work are as follows. We observed that participants typically use the walls for presentation, storage, and presentation purposes. Meanwhile, tabletops are only viable provided if they had some express purpose. It will be good to then investigate whether this applies to user-defined surfaces, and if it creates emergent use cases and workspace configurations. Groups naturally divided the shared room into personal territories while still ensuring proper workspace awareness. While this is the case for co-located collaboration, it is still unclear if this still applies to remote collaboration. Lastly, it was clear that presentation is challenging for many of our participants, particularly when dealing with 3D visualizations. Future work may aim to resolve this problem. Thank you for listening.
Thank you, Benjamin, for this presentation. And we have a couple of questions already coming up in Discord. I think one has been answered already by Tim Dwyer. So I picked the second one, which is just curious. Did you put a physical table there as well, like aligned with the virtual one, but the participants can physically touch it? If not, any insights that the physical one may affect the performance?
So we didn't end up putting a physical table there because we didn't really want to both have to align it as well as risk participants actually bumping into it and hurting themselves. We kind of took that same idea from other work, I think by Krauss and colleagues, where they also did a similar task with actual virtual table. But in that case, they explicitly said to the participants, don't walk into the virtual table. In our case, we didn't. In terms of how that might affect user performance, I can't really say for certain without trying it. Of course, there's this kind of mental effect where people will be a lot more apprehensive of moving into it because obviously then they'll hurt themselves. But it's kind of tricky to say without actually trying it, I suppose.
Okay, then I pick one more question, and that's what advantages did the co-located setting have over a remote or distributed one?
Yeah, so it's a bit awkward now for it to be co-located, especially with COVID now that we're all remote. But I suppose the main advantage of it is mostly has to do with the voice and the kind of the proximity that users have between each other, where you're standing and where you hear the other person's voice. That's as accurate as it can be because that's it in reality. And there's also sort of the social presence of there being people in the same environment. We did, as a matter of fact, kind of use the virtual reality environment as a kind of a proxy for AR, because at the time the HoloLens 1, where the HoloLens 2 wasn't out yet, but the HoloLens 1 obviously has a bit of issues with FOV, so this was kind of the best replacement. So that's kind of why we went that way. But of course, the next future work will obviously be looking at how users behave in a remote working context. So.
Okay, unfortunately, we already ran out of time for more questions, and there were many questions now popping up in Discord. So Benjamin will be there and answer your questions directly in Discord. And we go on to the next presentation, which is personal augmented reality for information visualization on large interactive displays, presented by Patrick Reipschläger and Tamara Flemisch from the Interactive Media Lab from TU Dresden.
We present our paper on personal augmented reality for information visualization on large interactive displays. This is work done at the Interactive Media Lab at the Technische Universität Dresden by me, Patrick Reipschläger,
and me, Tamara Flemisch, as well as Raimund Dachselt. We propose to combine large interactive displays and personal head-mounted augmented reality for information visualization. Large displays have shown to be beneficial for interactive information visualization. They offer natural touch and pan input, can be used by multiple analysts at the same time, and allow showing a large amount of data in high resolution. However, visualizations on large displays also pose several challenges regarding perceptual issues, managing data and complexity, and multiple analysts disturbing each other. In contrast to large displays, personal head-mounted augmented reality displays support spatial immersion and embodied interaction. They further allow for personal views for each individual analyst and can utilize the space around the display to visualize additional data. However, AR HMDs are intrinsically single-user displays and often use mid-air interaction, which lacks tactile feedback and precise input. We propose to combine a large interactive display with head-mounted personal augmented reality. This combination mitigates the individual limitations of each modality, while simultaneously strengthening their advantages. We call this combination augmented displays.
We imagine one or more analysts in front of a large vertical interactive display which shows one large or several linked visualizations of multivariate data. Each analyst wears an AR head-mounted display which is used to overlay the screen with additional user-specific information. The display serves as a frame of reference for all AR content and facilitates natural pan and touch interaction. Augmented reality, however, can help to guide analysts' awareness, show remote parts of the screen, and to display additional content directly embedded in the visualization.
We position our work on the intersection of research on large interactive displays, mixed and augmented reality, and information visualization. Besides the seminal work by Feiner and Shamash on hybrid displays, recent work has explored the promising combination of displays and mixed reality, such as Symbiosis Sketch by Aurora et al. Researchers have independently explored the use of large displays and mixed reality for visualization. How large vertical and horizontal interactive displays support data analysis has been thoroughly researched in the past, whereas the use of mixed reality technologies is currently being investigated in the emerging field of immersive analytics. Among projects that combine all three aspects and thus are highly related to our work are Art by Butcher et al., Data Space by Cavallo et al., and Sun et al.'s work on information sharing with AR and wall-sized displays.
Based on this related work, we contribute a design space for combining large interactive displays and augmented reality for information visualization. To illustrate this design space, we designed and implemented several visualization techniques. Furthermore, we developed a visualization framework with which we implemented our prototype and techniques. We validated those techniques with a use case scenario. Our design space consists of the spatial alignment of AR content in relation to the display, which parts of a visualization can be augmented, and how to provide personal content in multi-user environments. This design space can be used to inspire and guide the development of new visualizations and interaction techniques. We identified 9 different spatial zones where AR content can be placed. Each zone extends orthogonally from the display to include content that is in front or behind the display. Each part of a visualization can benefit from being extended with augmentations, such as data marks, links, and even whole visualizations. Those parts can be used to present additional, potentially multivariate data and to allow for personal annotations and tools. The combination of large displays with personal augmented reality allows for public as well as personal views for individual analysts. Those personal views can be used to prevent obstructing other users, provide personalized views, and display private information. This was a quick overview of the design space. More details can be found in our paper. To illustrate and explore our design space, we designed and implemented several techniques, which we will present in the following. We categorized them in techniques that mainly address issues with perception of data on large displays and techniques that help managing density and complexity of data. Furthermore, all techniques also provide user-specific content using personal AR HMDs. With our first technique, we propose to display additional data in AR directly on the corresponding data object to minimize context and focus switches. These embedded AR visualizations extend orthogonally from the display and can be of any type or shape. They can either be toggled or be shown on demand with a tap gesture to ensure good readability of the original visualization.
To reduce perception issues caused by extreme viewing angles and to support awareness for remote parts of the display, we propose to rotate visualizations in AR towards the user, similar to a hinged door. The larger the distance to the analyst, the more visualizations are rotated until they are orthogonal to the display. They hinge back towards the display as users step closer and ultimately vanish to reveal the original visualization on the display.
Similar to hinged visualizations, the curved AR screen addresses perceptual problems by curving the whole screen instead of individual visualizations. True curvatures extend left and right from the user's current position. The curve varies in size depending on how close analysts are to the borders of the display and from the distance to the display. As users step back, the curvature vanishes to provide an unobstructed overview of the whole screen.
Brushing and linking is a common technique to visualize connections between multiple coordinated views. To increase awareness of distant visualizations, we propose to show connections as VIS splines in AR space. The links can even encode additional values using color and the height of the curve. To reduce visual clutter, links can be shown on demand, for example by touching a specific data mark.
Large, dense visualizations can be overwhelming and make it hard to identify patterns. We propose to use the axis of a visualization to show a corresponding aggregation of the data to make it easier to explore a visualization. These extended axis views can also be toggled, shifted, and tilted by analysts to improve readability.
To reduce overplotting or to incorporate additional data, we suggest showing additional visualizations of the same type in front or behind the display, allowing for superimposed comparison between them. Alternatively, a single dense visualization can be split into multiple layers stacked onto each other to improve readability. Analysts can change which layer is currently visible on the display by interacting with it.
Even tools like magic lenses can be transferred into AR space. Thus, they no longer take up screen space and obstruct other analysts. Furthermore, the tool now becomes personalized and can be configured according to each analyst's individual needs.
Annotations, notes, and sketches can be transferred to AR as well. Again, they don't obstruct others when analyzing data and remain private to each individual analyst. We suggest to utilize natural pen interaction on the display to create annotations, while showing them solely in AR space. All of the techniques you've seen are individual techniques and work perfectly on their own. However, many of them benefit from being combined and complement each other, such as links, hinged, and extended axis views. To validate our techniques, we created a cognitive walkthrough exploring an IMDb movie dataset in a multiple coordinated views environment. It is described in detail in our paper and involves tasks such as identifying clusters using extended access views, creating user-specific annotations in AR, comparing movies of different genres using embedded visualizations, and guiding awareness to connected visualizations by using AR brushing and linking, as well as hinged visualizations.
To implement our visualizations and techniques, we created U2VIS, a data-driven framework for information visualization for Unity, which natively supports augmented reality applications. It can be configured completely in the Unity editor, is easily extendable, and available on GitHub. Based on this framework, we implemented our prototype. It consists of two separate Unity 3D applications. One controls the content on the display, while the other is responsible for the augmented reality content. We use a Microsoft HoloLens as an AR HMD, as well as for tracking and the spatial alignment with the display. The two applications' state is synchronized by a custom client-server solution using TCP and OSC. Furthermore, we provide a discussion of various topics such as the perception of AR content and the display, the advantages of combining immersive and display environments for data analysis, the influence of the alignment between AR content and the display, how to handle collaboration between multiple analysts, connections between multiple visualizations in AR, and the further potential utilization of augmented reality. Again, details can be found in our paper.
We presented our work on combining large interactive displays with head-mounted personal augmented reality for information visualization. We contribute an extensive design space, multiple visualization techniques, and our universal Unity visualization framework. We count this work to the larger class of augmented displays, which addresses the general combination of interactive surfaces with mixed reality, and hope to inspire future work in this domain. This concludes our talk. For further information, please visit our project website. And with this, we thank you for your attention.
Thank you very much for this very inspiring presentation. I have now Patrick and Tamara here, ready for taking questions. And I will just read out the first question, which is, does everyone see the same augmented views or were they user-specific?
Yeah, currently the augmentations are user-specific because we explicitly wanted to focus on personal augmented views so that we can have each analyst have a different view of the data, basically. But we also were planning, this is actually not implemented, but conceptual, that they can be shared between more than one user. But everything has to be explicitly shared, not shared.
Okay, another question is really cool work. What if you also provide a feature to hide unused or non-relevant plots on the wall to avoid overwhelming users, for instance, by overlays via AR?
It's an interesting idea, but diminishing reality with augmented reality, with see-through augmented reality glasses currently is kind of hard to do. So while you can conceptually, you can do a lot in this regard, but technically, I don't think you have any chance to actually make this work. Sorry.
At least not currently.
At least not currently, no.
Okay. Another question would be, I would love to hear a quick summary of the evaluation. Overall, what worked, what did not?
Most of the stuff worked kind of well. What didn't work so well, we usually had some concepts where we would have a lot more information in front of the display, and users would frequently just stay inside them, and of course you cannot perceive them very well. So a takeaway message would be to have a kind of a sparse AR content in front of the display, so it actually enhances your experience and not disturbs it. This is one of the main takeaways that we had. Maybe not a surprising one, but interesting nonetheless, I guess.
Okay, then thank you very much again for the presentation. The question and answer time is already over. I think there's still one question which has not been answered. If you have more questions, please post them to Discord. And we will continue with the next presentation, which is Vria, a web-based framework for creating immersive analytics experiences. And the work will be presented by Peter Butcher from Bangor University, and it was done in collaboration with the University of Chester.
Hello, and welcome to our presentation of Vria, a web-based framework for creating immersive analytics experiences in virtual reality. Motivated by the recent emergence of affordable, commercially available VR head-mounted displays and support for these devices in web browsers, our aim was to create a framework that would enable developers with varying levels of programming and visualization expertise to create consumable, interactive, and immersive data visualizations using standards-based web technologies. The web is the most ubiquitous, collaborative, and platform-independent way to build and share information, and thanks to the recent standardization efforts in the domain of the immersive web, by creating Vria as a native web service, we can use and share immersive analytics experiences with more people on more devices than ever before. Vria is built upon WebVR, now WebXR, an open standard allowing us to implement XR experiences in a web browser on many different devices. Vria also uses A-Frame, an XR content creation library for the web, providing high-level abstractions over the WebXR and 3GS APIs. Finally, we use React and D3 to handle presentation and data transformation. Following on from early preliminary investigations using these technologies for creating immersive visualization applications, Vria has evolved into a framework with a visualization creation workflow designed to be accessible to novice and expert users alike, by providing different yet complementary workflows to rapidly develop immersive analytics experiences for the web. At Vria's core is a declarative grammar described in JSON, akin to those of DXR and Vega Lite. We chose the declarative grammar approach due to its conciseness and expressiveness, as well as its wide adoption in other systems. Vria currently supports tabular data formatted as JSON or CSV, and supported visualization types currently include Cartesian plots such as scatter plots and bar graphs. In its most basic form, a visualization configuration, or visconfig, consists of a dataset, the type of graphical marks to use, and a set of visual encoding channels which map to individual data points. For instance, we can map data to the X, Y, and Z spatial variables, as well as a mark's dimensions, rotation, color, shape, and opacity. To keep visconfigs concise, missing values are inferred with sensible defaults tailored for optimal presentation and comfortable viewing. Once the visconfig has been passed and the data has been mapped to visual marks, the visualization is constructed with appropriate axes and legends before being added to the scene. Furthermore, any interaction controls for filtering and detail on demand operations are tailored to the hardware and viewing conditions at runtime. More on that in a little while. For beginners, or for those wishing to experiment or learn to create immersive web-based visualizations, we created a building tool called the Vria Builder, which is available on the project's website and also as an example project inside Vria's Node.js package. First, a user can load in a dataset that they wish to visualize, or choose to remix an existing visualization from a number of examples. Next, they can choose to create Vria visconfig with either the JSON editor or by using a drop-down builder for simple visualizations. With easy access to the Vria documentation, the builder serves as an end-to-end tool for learning, creating, and viewing immersive data visualizations, all from a web browser. Vria is a Node.js module, which exposes a React.js component plus an API for extended functionality. Vria can be integrated into existing web applications, with the only requirement being that the virtual environment into which visualizations are placed should make use of an A-frame scene. Other A-frame and 3GS components and assets may be included as part of a scene. For instance, a user may wish to create a virtual office space or a sports pitch onto which they can overlay visualizations. For more seasoned developers and visualization experts, and for those wishing to create more bespoke scenes for immersive analytics applications, Vria's Node.js module can be included in new or existing projects. Vria VIS configs that were created with the builder can be used directly inside the application code, and extra functionality can be added to immersive scenes with Vria's API. These workflows allow Vria to be used by novices and experts alike. Now, let's see Vria in action. The following demonstrations were recorded natively on an Oculus Quest using the Oculus browser, which now has full WebXR support. With Vria, you can create simple 1, 2, or 3-dimensional Cartesian plots using configuration files similar to those of Vega Lite. 1- and 2-dimensional plots can be useful in linked view applications. They are created in Vria by mapping data fields and their corresponding data types to the X, Y, or Z encoding channels. Here, a user is inspecting an immersive 2D bar chart of Welsh precipitation data. The chart layout and colours have been inferred by the Vria grammar and can be altered by adding additional properties to the visconfig if desired. Here, a user has created a 3D scatter plot of the iris flower dataset. We apologise for that, and has encoded 3 of its features to spatial variables and the flower species to the colour encoding channel. Axes, labels, and legends are all set up automatically and can be tailored further by adding additional properties to the visconfig if desired. Filtering, selection, and details on demand interactions can be enabled in charts via the visconfig. Here, a user has added a legend toggle filter, constraint-based filters to each axis, and a tooltip interaction. Any selections that are made in the visualization are accessible via Vria's API for external manipulation. Furthermore, bespoke interaction and UI components can be created with A-Frame and Three.js and linked to visualizations with Vria's API. The sorts of interactions that you can create are limited only by your imagination. A-Frame and Three.js assets can be added to scenes to situate data. Here, a user has created a tennis court asset and has overlaid a link view plot visualizing the service game of 2 tennis players. Visualizing data in this way could provide a better understanding of the data than if the points were presented as regular side-by-side scatter plots. Linked view applications are not limited to just 2D plots, however. Here, a user is interacting with a linked view visualization of car data. The results of filtering interactions in either chart are reflected in all other visualizations in a scene. Additionally, this visualization makes use of custom visual marks. A simple car model has been imported with Vria's API, and data has been mapped to the color, width, height, and depth visual encoding channels. Here, the user is using the tooltips, legend toggles, and constraint-based axis filters, and seeing the filtered results in both charts. Although Vria currently focuses predominantly on VR, we have experimented with augmented reality as well. Our intent is to integrate more mechanisms that facilitate other XR flavors in future as the standards governing them mature and improve. This example was captured on an Android smartphone. Although Vria offers sufficient built-in flexibility to design basic charts for many different applications, designers may wish to alter certain characteristics of their visualizations and customize them further. As well as adding bespoke interactions, applications that use Vria can benefit from integrations from other JavaScript libraries, for instance for networking. Vria's API can be used in conjunction with WebRTC, Socket.io, and many others to provide visualization and avatar synchronization between multiple clients in an immersive scene when any of the connected users move or make an interaction. As demonstrated, Vria currently supports Cartesian plots where data points are represented in a bar graph or a scatterplot structure. The range of possible encoding channels that these plots support beyond X, Y, and Z allows for the visualization of high-dimensional datasets. We plan to add support for other coordinate systems, an extended data model with more grammar features including some of the more advanced transform functions present in Vega Lite. While some experimentation has been conducted using Vria, we also plan to evaluate it further with a longitudinal assessment of the framework's UX from the point of view of developers and end users. Furthermore, although creating an application for immersive analytics with Vria is possible without leaving the browser via the builder, we would like to streamline this process further by allowing the creation of visualizations entirely from within VR. Maintaining adequate frame rates while rendering high numbers of data points is one of the most challenging aspects of building a VR experience. A web browser's resultant frame budget is typically 16.6 milliseconds for a common 60Hz display, but for a VR scene using a HMD, however, the frame budget will be 11 milliseconds if the device has a 90Hz refresh rate. A Vria performance profile using different devices demonstrates the challenges inherent in web-based VR, with frame rates dropping significantly after 1,000 data points for non-mobile setups. While Vria does incorporate its own optimizations to improve performance, further optimization is needed to increase data size without significantly impacting frame rates in interactive, immersive, web-based visualizations on less powerful devices. As we've experienced during the development of Vria, the synergistic use of established visualization libraries such as D3JS with Vria can be an enabler for the visualization community, allowing more opportunities for investigations and application development. Vria and its outputs can be interoperable, shareable, or even consumed by other tools via the DOM, as demonstrated by our very own Builder tool. It is important to emphasize that standards-based web technologies for VR and MR are inevitably not as mature as those found in the game engine ecosystem, for example. WebXR is still an experimental technology whose standards are constantly adjusting as it develops and matures. We therefore acknowledge that immersive technologies for the web are just past their infancy, and it may take some time before they are easily deployable. Nevertheless, we believe that their potential for VR or MR-based immersive analytics is significant and therefore worth the effort to explore further. Today, you have seen a brief overview of Vria, a framework for building immersive analytics solutions in VR, using standard-based web technologies. The resulting VR solutions can be experienced through a WebXR-compliant browser on a variety of devices and platforms. We have seen uses of Vria's declarative grammar, visualization creation workflow, and the API for extensibility. As the interest in immersive data visualization increases, there is a clear need to investigate and devise appropriate visualization techniques tailor-made for immersive 3D graphical environments. We believe that Vria is in a position to facilitate such investigations, and we cannot wait to see what you come up with. Vria is available free and open source at github.com/VriaJS. For more details, please check out our paper. Thanks for listening.
Thank you, Peter, for the presentation. We have a couple of questions on Discord. There were some questions concerning the limitations in terms of performance with respect to data size, especially if you can explain the drop in performance at 1,000 points.
Yeah, so the experiment we ran for the performance profile for data points over 1,000 points was using a kind of what we'd consider to be kind of a medium quality sphere with around about I think it was about 60 faces per sphere. So when you consider that the amount of geometries that you're rendering increases as the data size increases, then without doing more kind of mesh merging and things like that, which limits the interactions currently and things like that, we saw a drop off around about 1,000 on higher on more powerful devices. So yeah, with better work there, I think we can definitely improve it. And yeah, if you're using things like cubes for marks, then you will notice that you'll get more data points out of it and things like that.
Okay, you were mentioning the events, so there was a question about this as well. Does Vria use native JavaScript event calls, or does WebXR have its own event system?
So Vria makes use of A-Frame, which is the XR content creation framework, which is quite prevalent in the WebXR space, and we're using for now, we're using A-Frame's event system almost primarily. In future, we'd like to remove that step if possible and move closer to native JavaScript and WebXR calls. But for now, we do rely heavily on A-Frame's event system.
Okay. This is an amazing audience. We have so many questions that I cannot even ask all of them for every presentation. Keep on doing that. I love it. But we have to stop here now so that we stay on time. There's still at least one open question. So please look into Discord and you can answer the questions also there. And we go on to the next presentation, which is Uplift, a tangible and immersive tabletop system for casual collaborative visual analytics. And the paper will be presented by Barrett from Monash University, and the work has been conducted also in collaboration with Autodesk.
Hi, I'm Barrett Enns from Monash University, and I'm going to present this highly collaborative project with these many co-authors listed here called Uplift. Uplift was inspired by the Monash Net Zero initiative, which has an ambitious goal to reduce carbon emissions to zero by 2030. Now, this requires a substantial increase in self-generated renewable energy, as well as an increase in storage capacity, and initiated the development of the Monash Smart Grid. The Smart Grid is on Clayton campus, which is here about 20 kilometers southeast of the center of Melbourne. And right now they're currently developing phase 1 of the microgrid, which involves this subset of campus buildings that you see here. So there's a need to understand many different types of data, including the energy consumption of buildings. Of course, dashboards are a very common way to visualize and monitor energy consumption. However, we wanted something that's much more engaging and interactive than dashboards allow, because the smart grid systems in general are highly complex systems that involve many different layers of data that needs to be explored, and as well as understanding the individual data in each of these layers, is need to understand the interplay between these layers as they're interdependent, and changes in one can have effects on the others. So we took an immersive analytics approach, and this is following prior work such as Hull and Willett that we see here, which use 3D building models to provide a visceral experience and allow tangible and embodied interaction. So this is our system Uplift that we've designed to support what we call casual collaborative visual analytics. And this uses engaging tabletop interaction, tangibles, and augmented reality, and combines these together to create this collaborative experience for data exploration and knowledge sharing. So Uplift was designed through a co-design process that involved 10 different domain experts across expertise of microgrid project and energy systems. And this process lasted about the duration of about 1 year and involved some initial interviews, an initial problem elicitation workshop, and iterative development cycles, including 2 formative workshops with the domain experts. So the initial interviews and elicitation workshop helped us to identify many key problems in the domain and helped us to understand the scope and complexity of the microgrid system. So as I mentioned, we call this approach casual collaborative visual analytics, which through the workshop and interviews, we developed 4 design criteria to support this. So the first one is to create a walk-up and use system that's very just accessible to a variety of different types of users. And of course, they have these users have varying degrees of technical knowledge. So there needs to be a low barrier of entry to make it easy for those users to use the system. So it needs to be available and easy to use, and support multiple participants. So of course, it needs to be collaborative, and it needs to be flexible to support either small groups of 2 to 3 or larger groups of knowledge holders, including company executives or visiting clients. And It needs to support bursts of analytic activity lasting from about 5 to 20 minutes. So to implement these guidelines, we use a number of technologies that I mentioned: a tabletop display, tangible widgets, and augmented reality displays. So the tabletop display provides an engaging centerpiece for collaboration. This contains an interactive model of the phase 1 of the microgrid, which I showed. And this physical model acts as kind of provides a physical reference for people to understand the geographic layout of the campus, and provides acts as a referent to enable what we call embedded visualization. So embedded visualization puts the data representation directly onto overlaid on the building. And you can see here that the energy use is encoded for each individual building by color. So the brighter orange buildings are using a higher amount of energy, and the light buildings are using less energy. And of course, the tabletop provides a physical input surface that allows different overlays like you see here, or other types of information such as the grid infrastructure and so forth to be displayed alongside the physical buildings. Now, this system uses tangible widgets to provide a playful way to interact with the system. We noticed right away that when users see these models, they have a natural urge to pick up these buildings. So we use a Vicon tracking system for prototyping in this project. And we implemented tangible widgets to allow intuitive interaction with the various system features, including this time granularity widget. Now this allows users to kind of drill down into time. So starting with a yearly view, they can drill down into monthly, weekly, daily, or hourly views. And users can interact with these sliders to kind of see an animated view of how energy changes over time within one of these granularities. And we also introduced this time slider widget. So this prototype widget allows kind of a physical prop that users can pick up. Instead of controlling the time slider on the tabletop, they can use this widget, which is a little bit more engaging, and also allows collaborative exploration. Different users can control different widgets and kind of work together in their exploration. So finally, we use augmented reality displays to allow users to view data above and around the tabletop. So we use this HoloLens display, or multiple HoloLens displays actually. And these allow things like this space-time cube view. So this provides a snapshot of a time interval with time in the up direction. And by holding the time slider and kind of flipping this up, this acts as a mode switch that switches from the tabletop surface animated view to the space-time cube view. Now, unlike so this is what it looks like here. And you can see a user switching into a granularity. So this is the hourly view. You can see there's many time slices. Each slice represents 1 hour of data within the chosen day, and so forth. So unlike the tabletop display, which allows you to kind of see an average over the chosen time period, this provides a little bit more detail. So within that chosen day, you see the average of the day on the tabletop, and then you can see the time of day within this kind of hourly granularity. So you can see daytime usage in these buildings here was very high, so blue is higher energy use, and this building over here has a higher energy use in the evening. So it lets you kind of see that granularity a little bit more and compare different time periods between different buildings. So users can also see building-specific data, such as the learning and teaching building that you see here. This building is very modern with a lot of sensors integrated into the building. And So when the users pick up this building, they can see a model representation of that building. They can manipulate this in 6 degrees of freedom and also see additional data about floor space allocation and energy consumption from different systems within the building. We also had some data from solar energy systems within the campus, including some weather data about solar intensity, cloud cover, and electrical generator from the solar cells. So this is a view of the data produced by the solar arrays. So the bars that you see when we go into solar mode, the bars represent energy generated by the various campus buildings, and on the back there's a traditional 2D display of some weather data, so you can kind of compare a slide through time and see the weather data relative to the solar generation within the chosen time frame. So we had 2 feedback workshops, 2 sessions that gave us some formative input into the project with our co-design experts. We had 2 sessions with 2 groups each, so one in April of last year and one in September, and these included members of Monash Energy and the Monash Buildings and Property Division. And they were, in general, very positive about the system. So you can read the full results in the paper, but in summary, the experts were able to see some promising applications of Uplift. For instance, they thought it would be useful for sharing knowledge between users with different knowledge sets, and to help educate energy users with visual storytelling. And they thought the system can provide a high-level overview of the system's complexity for energy operators. Of course, there's some next steps with the system. This is an initial prototype that we use some pre-existing data because the microgrid is not online yet, but as it comes online, we'd like to incorporate some real-time data into the system and explore this with more users and scenarios. We'd like to build a self-contained system that doesn't rely on the Vicon tracking system, include additional features like simulation and forecasting to produce some useful modeling, and of course do some longer-term studies with deployment in the wild. So just to recap, we present Uplift, which is a system to support casual collaborative visual analytics. This was designed in a co-design process with several smart grid experts. It combines multiple technologies that help to break down knowledge silos and educate energy users, and the system provides an intuitive overview for identifying patterns. Thanks for watching.
Okay, thank you for this very interesting presentation, very interesting combination of techniques and very inspiring application. I have Sarah Goodwin here and Arnaud Prouzeau who will answer the questions, and I will just start to read them out from Discord again. And I'll start with the first question, which is, how does the backlight on the tabletop interfere with the AR overlay? Are there additional design constraints created by the interaction between devices?
Good question. We spent a long time trying to get all these things working together. The backlight doesn't interfere too much, and the AR layers are slightly above the tabletop, so you can see everything underneath as well, but they're associated by the building shapes, so you can associate the overlays with the buildings by where they're positioned.
Okay, the next question would be brilliant work. How many of your designs do you feel can be transferred and or easily adapted to other use cases and contexts?
Quite a few, I think. We've been speaking to a few people. We showcased the case in a few places. So we've had a couple of conferences where we went to, different, mainly energy conferences, but people have also approached us and interested in doing things like mapping scenarios and mapping models of things like flood scenarios of different situations. Maybe if you can put the seawall and different objects onto the tabletop, or in a similar way, you could show those effects quite in a similar manner.
Okay, unfortunately, short Q&A is already over again. There's a couple of more questions. Some were labeled as lame, but also very interesting questions. So please have a look in Discord and answer them there so that we can proceed to the next presentation, which is revisited comparison of empirical methods to evaluate visualizations supporting crafting and assembly purposes. And the paper will be presented by Katrin Angerbauer from the University of Stuttgart.
Hello everyone, my name is Katrin Angerbauer and I'm doing my PhD at the University of Stuttgart. On behalf of Maxime and VIS and all my other co-authors, I'm very happy to present our paper, Revisited Comparison of Empirical Methods to Evaluate Visualizations Supporting Crafting and Assembly Purposes. Don't get scared by the long title. Nowadays we're able to present visualizations in ubiquitous settings. Situated visualizations are context-aware and directly integrate their surroundings. Thereby they provide the user with additional semantics. Whether or not the visualizations are actually perceived as helpful, we should evaluate empirically. Here we have a multitude of choices. Online surveys enable us to get fast feedback and at a low cost. VR studies might especially be handy if we evaluate scenarios that might be too expensive or even too dangerous in real life. For example, if you evaluate some medical settings. Lab studies, of course, provide us with the most control over our experiment design and setup, while in situ studies have the possibility to directly evaluate the visualization where it is used, for example, in people's homes or at their workplace. But does the choice of method matter, or can we, especially now in COVID-19 times, where it's difficult to run a lab study, instead just switch to an online survey and get the same results regarding the subjective feedback of the participants? Or does the method actually have an influence on that? Voigt et al. In the HCI domain especially investigated this issue. They asked about the influence of the method on subjective feedback from the participants when evaluating smart objects that you can see here in the video. And they looked at online, VR, AR, lab, and in situ conditions. Interestingly, Voigt et al. Indeed found that the empirical method seemed to influence the results of their usability questionnaires and the open feedback. Here you can see one interesting example of the attractive questionnaire. Here you can see that in the online and lab condition, people rated the prototype rather neutrally, while in the in situ and VR condition, they seemed more excited about it. But it was the same prototype. These results intrigued us, and we asked ourselves, are empirical methods interchangeable for visualizations, or does the effect that Voigt et al. Measured also occur here? To shed some light on this issue, we implemented 4 visualizations for do-it-yourself tasks, which I will show you in the following videos. In the assembly tasks, we asked the participants to assemble a chair. The parts the participants had to take was highlighted with projections, and also the position the part had to go. If the participant made a mistake, it was also highlighted accordingly. These visualizations were based on work that was previously done by Funk et al., which also used projections to help participants assemble something. In the drilling task, we got inspired by a previous work from Heinrich et al., who used crosshairs visualizations to help the injection of needles. We adapted that for drilling tasks and helped the participants regarding the angle and the position of the drill. And we also provided some feedback regarding the drilling depth. As you can see here in the video, the crosshairs slowly fill with color, the deeper the hole gets. For the sawing tasks, we also provided a position indicator and a visualization for the saw angle, so the participants could saw rather straightly. This was based on work by Schub et al. For the placement of the screw, we again used the crosshairs visualization, and to provide feedback on the depth, we used a bullet visualization, and the participants ideally had to go on with the task till they reached the green line. All these visualizations were implemented for Unity. Our study design was the following. We had a mixed design. That means we had one in between subjects variable and one within subjects variable. So a participant, for example, only experienced the online condition, but he or they experienced all 4 visualizations. We measured the same as Voigt et al. Because we were primarily interested in the usability ratings and the subjective feedback. Therefore, we used standard usability questionnaires, such as the system usability scale, where participants can rate the usability based on different characteristics, and the attractive questionnaire that I mentioned before, and the ARI is just there to rate the participants' immersion into the task. And additionally, we asked open questions concerning our visualizations. We had 60 participants in total, and we made sure that age and gender were balanced across conditions, and our participants aged from 18 to 63 years. So we had quite a wide age span. Let me quickly show you the study setup. We used a Wizard of Oz approach. So there was always an experimenter standing next to the participant and looking what he's doing, and then adapting the visualization accordingly via the app, which you can see here. In the online condition, we recorded someone doing a task and showed these videos to the participants, and those videos were 30 seconds long. Our results are in contrast to Voigt et al., so we did not find a significant effect of the method on the questionnaire responses, as you can see here in the graphics. Our word count of the open questions, however, was significantly impacted by the method, which is also in line with findings of Voigt et al. So for the VR condition, participants answered significantly more than the online condition. WordCat isn't, of course, telling us everything, so we also looked into the content of the feedback we got in the open questions and did some affinity diagramming to find out common topics and themes. And interestingly, our questions only concerned visualizations, but 25% of the time the atomic statements were based on the technology the participants experienced. Like, I don't like the heavy helmet on my head, or no real sensation, no haptic feedback, which has nothing to do with the visualization itself, but only with the technology the participants experienced. But other than that, our results were not influenced by the method or the technology, luckily. So we can conclude, in our paper, we evaluated situated visualizations using different empirical methods to test the effect of empirical methods. Our results show that, in our case, empirical method did not have an impact on the results, which is in contrast to Voigt et al. And that again stresses the importance that we should verify previous results before applying them to new domains, because results and findings might change. And our plans for the future are that we want to validate our results for a wider range of visualizations to make sure the method does not have an impact there as well. Thanks for your attention, and in case of questions, do not hesitate to contact me or my co-authors, and otherwise stay safe.
Okay, thank you very much for the presentation. And so far we don't have any question in Discord, but a lot of appreciation of the study design. I thought exactly the same thing. It would have been good for my crafting skills to participate in that study. So we'll start with a question, and maybe there are more questions than on Discord in the meantime. So your results do not support the previous results by Voigt et al. Do you have any suspicion why this might be the case? Any ideas?
So we discussed that also in the paper. So we thought maybe the novelty effect of smart objects was maybe a bit more in previous study by Voigt et al. And which was maybe not the case for our study, but yeah, it's difficult to say, and that's why we also wanted. So the effect that we had by the previous study in Voigt et al. Is quite intriguing. You know, if you get different results from different methods, so we wanted to validate that as well. So yeah.
Yes, I think that's very important as well.
Yeah.
So there's a comment on Discord. No questions, but a comment. Everybody can see the use of this and wants one. Keep going. So I can only underline this. You didn't measure the task performance. Could this have been done, or do you think that could have provided additional insights or explanations?
Yes, of course, task performance could have provided additional insights, but we wanted to compare, all those 4 methods, and you cannot measure task performance when showing the visualization online, and we were primarily interested in subjective feedback. But if you want to measure, the visualization itself or the performance of the visualization itself, you of course should include the task performance, but yeah, we were primarily interested in comparing the actual empirical methods.
Okay, that's already the end of the Q&A. If there are any more questions coming up, please have a look in Discord and you can answer them here.
Yes.
So we're coming to the last presentation of this session, which is Embodied Navigation in Immersive Abstract Data Visualization. Is overview and detail or zooming better for 3D scatter plots? And the presentation will be given by Yalong Yang from Harvard University, and the work was done in collaboration with Monash University.
Thanks for coming. My name is Yalong Yang from Harvard University. Today, we are going to look at how to navigate in an immersive visualization. This work is collaborated with Maxime Cordeil, Johanna Bayer, Tim Dwyer, Kim Marriott, Hans-Peter Fister. The display space is always limited and can only show part of the information. What if you want to go to a specific location outside of the current screen, like the marked one? Panning is a basic navigation method which allows you to go to different places. However, without knowing where to go, panning alone is not effective. Additional interactive support is essential. Zooming scales the view up and down. The user can first zoom out to an overview to identify the location of the target, and then zoom in to check the details. Another option is using Overview plus Detail technique. In an Overview plus Detail interface, we use a small window to show the full information space, and the rest of the display is used to show the detail view. As we can access the full information in the overview, we can easily figure out which direction we should move or pan. These navigation techniques has been extensively explored on 2D screens. Cockburn and his co-authors published a survey reviewing 2D navigation methods and user studies in 2008. There are also many papers after that. However, this research only studied navigation techniques on traditional 2D screens. But how about we enlarge the display space like a dozen times, and even with one more dimension? What interactive support should we provide for navigation? This is a problem we explored in this project. One obvious direction is looking at these 2 well-established navigation methods and figure out how to adapt them into 3D immersive environment. Let us look at zoom first. There are 2 widely used zoom mechanisms, mouse scroll and pinch to zoom. Mouse scroll are commonly used on desktop, for example, Google Maps in the browser. Pinch to zoom uses the distance between 2 points to decide the scale. It is more common on touch screens. Both mechanisms are familiar to people. However, when using mouse scroll to control the scale, the motion is abstracted to a unit scale, while in pinch to zoom, the motion is directly mapped to a continuous scale. Meanwhile, pinch to zoom requires a multi-touch input system to work. Considering the embodied nature of an immersive environment, we choose to adapt the pinch to zoom method. We use 2 controllers as the multi-touch inputs. However, we found a new challenge. The knife pinch to zoom method only considered the scale of the object, but during the zoom, the user may also move and rotate the object. Only changing the scale may make the object away from the controllers, which obviously affect the user experience. To tackle this issue, we implemented a latched pinch to zoom mechanism, which allows the controllers to stay at the same relative positions to the object. Here, we demonstrate how we can zoom, rotate, and move a visualization at the same time in the immersive environment. Next, let's look at the overview plus detail. Following the basic idea of overview, we duplicate the full 3D immersive environment to a minimap. Although this basic concept is simple, there are many other design decisions for an immersive overview. For example, where we should place the overview. On a 2D screen, the overview is usually placed at a fixed location, for example, the bottom right corner. Following this idea, we attach the overview to the bottom right corner of the field of view and allow the user to pick it up. We piloted this idea with 2 participants. Both participants found the overview distracting and cluttered. We came up with another idea. We attach the overview to a controller, so the user can easily hide and access it with simple arm movements. We also shrink the size of the overview by default and allow the user to enlarge it by simply put another controller inside. The user can also grab the overview, move or rotate it, and see it from different angles. When creating an overview for a 2D visualization, it is important to indicate the region of the detailed view in the overview. Following the same idea, we created an object showing the real-time position and orientation of the user. This is useful for many scenarios. For example, here, the user noticed that the yellow target is on the left to the indicator in the overview. Then she can simply turn left to find the target in the detail view. We also allow the user to use the overview to teleport. Let us first introduce a drag and drop teleportation. The user can pick up the point of view indicator and move it to a new position, and then release it to teleport. We also provide another way to teleport, point and click teleportation. The user only needs to move the controller to the target he wants to see, and then click to teleport. We designed and conducted a control user study to understand the effectiveness of these different navigation methods. The baseline condition is the one without any support. We also have the zooming condition and the overview plus detail condition. We can certainly have a condition with both the zooming and the overview plus detail. In this condition, the user can rescale the view, move in space, and also take advantage of the overview to teleport. We also allow the participant to use the pointer teleportation in all conditions. We use the scatter plot as a testing visualization. We randomly sampled points from MNIST and used t-SNE to create the scatter plots. We identified 2 most fundamental tasks for scatter plot visualization that require the participants to navigate to the fine detailed information. The first task is to compare 2 distances. We also found that whether the user can see 2 points in a pair together may affect the results. So we have the close condition that the 2 points in a pair are close. We also have a condition that the 2 points are far away. The other task is counting the points. The participants were asked to count 3 groups of colored points and reported back the group with the largest number of points. We recruited 20 participants for our user study. We collected the time accuracy for each trial. We also recorded the moving distance and the number of interactions performed by the participants. Participants also reported their subjective ratings and rankings. Next, we are going to answer a series of questions with our collected data. The first question we would like to answer is having an overview beneficial? With the testing conditions we have, we can look at the 2 comparisons. We can compare these top 2. We can also compare the bottom 2. Let us first look at the top 2. The arrow bars are showing 95% confidence intervals. The dashed lines connecting bars are representing comparisons with significant difference. We can see that adding an overview can increase task accuracy in distance closed tasks. However, it also introduces extra time cost. We also look at the number of teleportation performed by the participants. We found having an overview reduced the number of teleportation in some tasks. We also asked participants to rate their confidence from low to high. We found participants felt more confident with an overview. Let us look at the other pair, zooming interface and zooming interface with an overview. We found having an overview for a zooming interface may not be necessary, as the performance was similar. Sometimes having an overview may even be disturbing for some tasks. Previous research found similar results on 2D screens for comparing zooming interfaces with and without an overview. Since having both zooming and overview was not effective, we will not include it in the following discussion. Please see our paper for details. The next question we want to answer is which interactive support is better, zooming or overview plus detail. We can see zooming was faster in the distance far tasks, while overview plus detail were more accurate in the distance close tasks. Looking at the participants' feedback, we found participants liked to have two scales of views and thought overview to be convenient for finding targets and moving around. However, some participants also commented that teleportation using the overview breaks spatial continuity as you suddenly jumped to a new place. On the contrary, in zooming, people liked the way it provides continuous navigation. The pinch to zoom gesture is embodied and continuous. However, people also complain that they need to zoom in and out many times. We then look at whether participants perform better with moving the object or move themselves in the immersive environment. We found participants were faster when moving themselves than moving the object. This partially aligned with the previous study, which found participants without much gaming experience preferred to move themselves in VR. Most of our participants classify themselves as not playing games regularly. In summary, we found adding an overview to the baseline condition can increase accuracy for some tasks. Adding an overview to a zooming interface seems unnecessary. Overview plus detail was more accurate than zooming interfaces in some tasks. Zooming was faster than overview plus detail in some tasks. Physical movement was faster than object manipulation in some tasks. We can see there is no clear winner for all conditions. From the results, we found the baseline condition performed generally well, especially in terms of time. However, when looking at the camera moving distance, we can see the baseline condition required significant more physical movement than other conditions. When looking at the number of teleportation, we again found that the baseline condition required more teleportation. We also noticed that baseline condition was ranked as the worst by our participants. Our participants complained it to be difficult for finding the targets. So all this should lead to extra time cost. However, the baseline condition performed generally well. We want to figure out what happened. We found that navigation is a complicated process with multiple components. We identified 4 components from the literature. Wayfinding is the process of finding the destination. Travel is the modal part of getting to the destination. Number of travel can be different in different conditions. Context switching is when the user gets into a new location. She needs to reinterpret the new environment based on expectation. We then analyze the performance of our tested conditions in each component. For wayfinding, we believe overview plus detail has the best performance, as the user can use the overview to find the targets at all times. Zooming with an overview also provides a minimap, but participants found it disturbing. In the zooming interface, the user can only zoom out to have an overview, so she cannot access the overview when looking at the details. In the baseline condition, the user does not have any support for wayfinding. We used our collected interaction data and the user's comment to analyze the travel and number of travels components. Due to time constraint here, we only present the results. Please see our paper for details. For the context switching performance, we believe the zooming interface has the best performance as it provides a spatial continuous experience. In the baseline condition, the physical movement also has a spatial continuous experience. However, participants also performed a significant number of teleportation, which introduces context switching cost. When teleporting with an overview, the user can hardly estimate the destination, which we believe has the highest context switching cost. Based on our analysis, we believe the overview plus detail interface has a great potential, as long as we can improve the performance in the number of travel and context switching. We proposed a few directions in our paper. Our navigation time cost model can also be used for task analysis. This is to understand which component is more important for a specific task. Please see our paper for details. In summary, we are the first to systematically explore overview plus detail and zooming interfaces for immersive visualizations. We conducted a user study comparing 4 navigation methods. We also proposed a navigation time cost model, which can be used to analyze navigation methods and tasks. Thank you very much for your attention.
Okay. Thank you very much for this very insightful presentation. And there are a couple of questions on Discord. The first question was that considered methods might be a bit complicated to understand. So can you comment a little bit on the training procedure that you did? And especially the question is whether a training in a realistic space could make sense here.
Thank you. That's a very interesting question. I assume the realistic space, you mean basically a AR space, like you can see your virtual or your physical surroundings. Is that what you mean? Sorry, my cat.
I guess that was meant, yeah.
So for the, I think that's a very interesting perspective, because actually this year there is a paper suggesting if you have more meaningful surroundings, it can help your spatial memory. So this can be a very good point. We did do a lot of training to make sure every participant can get familiar with all the techniques we used in the user study, and also with task trainings as well. Yep.
Okay, another question was, did you have any problem with motion sickness while introducing your new way to teleport within your overview approach?
Yes, that's, I would love to tell more details. So one thing is actually our testing space is not super large. It's like a normal office space. So people feel comfortably to move around. So they feel less motion sickness in that case, I guess. And also from the feedback, actually some of the participants pointed out the teleportation breaks the spatial continuity. And during the analysis, we figure out the teleportation no longer what teleportation you use, it will affect the context switching cost. And actually in the paper, we point out that can be a very good direction we want to go if we want to improve the overview plus detail in the future. And we pointed out a few future directions. For example, we can provide more continuous morphing to the new position instead of suddenly jump to there. And also a few directions in our paper. So please check our paper for more details.
Yeah, this has also been a question whether you considered interpolated camera movement. And another question in that direction actually is if there's any background work to suggest what style of teleportation would work best for visualization tasks.
Interesting. I think I saw a few papers that is interesting for when you teleport, you can actually indicate which direction you want to face after you teleport to the new place. So that can be a thing that can reduce the cost, context switching cost, I believe, because you can build kind of your expectation of the new place. Apart from that, I think the continuous way is another thing we can look at. And also, I think another thing is like there are objects that can outside of your field of view. And if you can indicate this object in a more meaningful way, you probably do not need to teleport that often. You know they are there, and then you can just do physical movement there. So I think the whole immersive experience is combination of a lot of things going on, and the user will never just use one method. We need to think about the way that we provide everything, and also I think teach the user how to use the system. That's my feeling. Yep.
Yes.
Thanks.
Thank you very much for answering these questions. I think there are a couple of open questions still on Discord. Thank you to all the speakers of this session and all the people that were here for the Q&A. Thank you also for the audience. This has been a very lively discussion. I really enjoyed it. And now I end this session and have fun at the VIS conference.
Thank you very much.
Region-based vortex measures are commonly used to extract vortices. The ideal threshold to extract the vortex boundary, however, varies spatially. To detect vortices without manual thresholding, we utilize supervised deep learning. For the regression, we evaluate 3 recent network architectures. The resulting networks are able to detect vortices that grow in size due to diffusion, despite their angular momentum becoming smaller.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
We present an efficient approach for volume and isosurface ray tracing of structured AMR data on GPU-equipped workstations, using a combination of 2 different data structures. Together, these data structures allow a ray tracing-based renderer to quickly determine which segments along the ray need to be integrated and at what frequency, while also providing quick access to all data values required for a smooth sample reconstruction kernel.
Exploring the emotions of students in classroom videos can help both teachers and parents know about students' learning status and further help teachers improve teaching. However, it is a non-trivial task to analyze the emotion evolution of a group of people from classroom videos due to 3 major challenges. We propose a visualization system which integrates the model uncertainty and supports both collective and individual emotion analysis.
The mixture graph is a data structure for compressing, rendering and querying segmented volumes. Biomedical segmentations have evolved from mere annotations to first-class modalities. The mixture graph stores the computations required to render such nominal data directly on the GPU, including pre-filtering and lighting. Segment distributions can be queried efficiently using regions of interest.
We present a high-quality tube rendering method for 3D line datasets. GPU-based raycasting is used to render line segments as rounded cones, to allow for smooth connections along individual lines and variation in radius. We support transparency by a novel approach combining visibility order rendering with an order-independent transparency method. To improve depth and feature perception, ambient occlusion is employed.
Visualizations are about visual patterns, but there's more, much more. We show the connections between more than 100 arguments on why visualization works. And don't forget to check out our website.
We introduce a direct volume rendering approach that can render encrypted images directly from encrypted datasets. The rendering is performed by operations in the encrypted number space which are dual to operations in the plaintext space. Therefore, the rendering system does not need to decrypt the data. This homomorphic volume rendering approach makes it possible to use untrusted servers for rendering without compromising privacy.
Traditional clustering tools do not include users in the analysis loop. We present PK clustering, a new approach for interactive clustering using VIS. First, users specify their prior knowledge. Several algorithms are run and match with the prior knowledge. Users then build a consolidated clustering iteratively with suggestions based on consensus, the graph, and their knowledge of the data. The result is a consolidated clustering.
We present columnar data augmentation through visual analytics. Kava lets users augment their data with additional attributes found on knowledge graphs. To construct a new attribute, each row of a dataset is mapped to a node on a knowledge graph. Each augmented datum is the result of a query over the knowledge graph in the neighborhood of that node.
Hey everyone, I'm Junhan Zhao, a PhD candidate at Purdue University, computer graphics major, and a research internship at Bosch Research North America. Here, we are presenting our recent research, Prouzeau, using factorized prototypes to visually interpret and diagnose deep neural network. This work is co-authored by research scientists at Bosch, Zhen Dai, Dr. Panpan Xu, and Dr. Liu Ren.
What do you believe is the correlation between labor union participation and corporate profits of different companies? How would you update your belief after seeing this scatter plot? In this study, we use a new elicitation technique to understand how people update their beliefs about correlations after seeing different visualizations with and without uncertainty depictions.
We propose data-driven space filling curves. Our new method generates linearizations that better preserve coherency than existing techniques. Our method supports 3D datasets, and even multi-scale data on a quad tree or an octree. Many visualizations benefit from our method, for example, visualization of multivariate particles, and visualization
to interactively explore and visually analyze large multivariate data. For example, this cosmological simulation that is clustered into dark matter halos. We create a probabilistic data model in each cluster. We present a complete visual analysis system based on this data representation, which is especially well suited for the density-based visualizations shown here.
Given a dimensionality reduction scatterplot, we project its original subspace. Through the orientation and shape of our glyphs, both the global trends and local patterns can be identified. To transform the vectors, we use implicit function theorem. We apply our method to different kinds of data.
We propose a multi-perspective simultaneous embedding (MPSC) algorithm for visualizing high-dimensional data based on multiple pairwise distances between the data points. MPSC computes positions for the points in 3D and provides different views into the data by means of 2D projections that preserve each of the given distance matrices. MPSC works on abstract data as well as graphs.
Visualizing the performance progression of machine learning techniques is often achieved by plotting the accuracy in a line chart. For specific tasks such as multi-class classification, They hide important factors such as inner-class confusion and instance-level details. We propose Instance Flow, a tool for interactive visualization of the evolution of classifier confusion on the instance level.
The transmission of pathogens such as bacteria and viruses is an acute problem in hospitals around the world. Infection control experts need to monitor infections and determine transmission pathways. We developed a novel visual analytics system for the exploration of disease outbreaks. It combines several interactive views and a tracing interaction that allows to detect pathogen transmissions.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Language models are highly performant across many language understanding tasks. Comprehending the linguistic knowledge encoded by these models, however, remains a challenging problem. We introduced an approach for visually analyzing contextualized embeddings produced by language models. Our design shows how much context is captured by embeddings, the ability of embeddings to capture meaningful text spans, and linguistic relationships represented by the embeddings.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
We present a framework for the visual exploration of spine simulation data. We show the force distribution on spinal discs, enable assessments of imbalances, and reveal impact vectors that were not accessible before. This is a novel direction in medical visualization, and we hope that it might bridge the gap between biomechanical research and clinical application.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
Hi everyone, I hope you're doing well. I'm Heikyu Park from Georgia Tech. I'm very excited to present Bluff, a visualization tool to interactively decipher adversarial attacks on deep neural networks. Deep learning is now commonly used in many domains. For example, in the medical field, deep learning models can estimate the treatment effects on patients. On the road, we can see self-driving cars using computer vision technologies. However, deep learning models are vulnerable to adversarial attacks. An adversarial attack applies carefully crafted perturbations on data inputs and fools a model into making incorrect predictions. Adversarial attacks jeopardize many deep learning-based technologies, especially in security and safety-critical applications, such as data-driven healthcare and self-driving cars. Due to the threats of the adversarial attacks, people cannot confidently use deep learning models. To overcome the vulnerability of deep learning models, we need to understand how the adversarial attacks permeate the model's internals. Also, for a better understanding about adversarial attacks, it would be worthwhile to examine if and how an attack strength changes how the model produces incorrect predictions. For example, it would be useful to know if a stronger attack exploits the same neurons as a weaker attack does, or if those sets are completely different. We present Bluff, an interactive visualization tool for discovering and interpreting how adversarial attacks mislead DNN into making incorrect predictions. Our main idea is to visualize activation pathways within a DNN traversed by the signals of input data. For given input data, an activation path